Alright guys, I'll be going through the questions in the exam, the past paper ones. The questions should be the same. If speculation is correct, Ben is on holidays and he's the one who's been designing these things, so if he's decided to be nice and not change anything up, the exam shouldn't be too bad. I'll be going through questions 1 through 7 except for 5 until I can figure out how to do 5. Yeah, it's just a pain in the ass right now. So yeah, let's do it. So basically, the first thing question 1 wants us is to work out VAB, which is just the voltage between terminals B and A, so it's VB minus VA. In order to work out the voltage at terminals here, points A, we need to do current division between both of these branches. In order to do that, we have VB equals IS times, shut up phone. Oh, god damn it. Sorry. There we go. Shut up. Okay. IS times, I'm doing VB, so I'm doing this branch first. This one here. We R4 plus R1 all on R1 plus R2 plus R3 plus R4. And obviously we're timesing that by multiplying by R3 again. This here is the current division, and this entire thing is just Ohm's law. Obviously V equals IR. Because if we find the current going through this resistor here, then the voltage going through that resistor, we find out what the voltage is at terminal B. So doing that, 6.2 E-3 6. Let's go just do the whole thing. That'll be everything on this branch divided by all the resistors all up, the equivalents. 6800 plus 2400 plus 3800 plus 2700 equals 15200, and then timesing that again by 2400, and that gives us VB equals 9.3 volts. Nice and simple. Now VA is just the exact opposite of what we just did. VA equals IS times R3 plus R2 on R1 plus R2 plus R3 plus R4 times R4. It's important to note that when you're doing this, you can either use both these or both these, but you can't use like diagonally opposite ones. It does not work. And that just equals 6.2 E3. Screw it, I'll just do straight there. You know how to sub in things. And now that is 15.81. Now VAB equals 9.3 minus 15.81 equals negative 6.51. If we go to check here, that is indeed the answer. Thank God. Okay, now the next thing it wants us to do is, I think it'll always want this. Let me just. Excellent. It'll always want this bottom resistor, but don't quote me on it, obviously. Yeah, what it wants is the value of R1 to make the VAB equal to 0. It's basically when VB and VA equal the same amount. And basically the way to work that out, the 0 equals VB minus VA. Now I'm going to go the long-winded way around this. There's a shortcut way to do it, but I'll go the long way. Hopefully it works out the same. I'm going to leave out IS because I can factor that out and then get rid of that altogether. So R4 plus R1 all on R1 plus R2 plus R3 plus R4 minus that times R3 minus R4 R2 plus R3 all on R1 plus R2 plus R3 plus R4. That's equal to 0. Now I will skip a step here. If I multiply these, expand these, it ends up being R3 times R4 plus R1 on top of this, and minus R4 times R2 plus R3 on top of the denominator. Both denominators are the same. Factor those out, multiply out, and you end up with R3, R4 plus R1 minus R4, R2 plus R3, and expanding these, R3, R4 plus R3, R1 minus R4, R2 minus R4, R3. Now this and this cancels, and if you take this onto the other side, you end up with R4, R2 equals R3, R1. Solving for R1 divided by both sides by R3, we get R4, R2 on R3. And if we check the thing here, R4 times R2 on R3, and that's our answer. Nice and easy. And to just get R1 numeric, we sub in our values for R4, R2, and R3. So we have R1 equals 6800 times 3300 on 2400. That equals 9350 ohms. Double checking. There you go. And it's solved. Nice and easy. I will save all of these. Probably should have made this beforehand, but who cares? New keyboard, still getting used to it. Alrighty. And why did I close the thing? No, I already did that one. Oh, bloody hell. New keyboard. Okay, file, new. Let's go with this one. Now you already know the explanation, so I'm just going to do the working. And I'll try and make conversation so it's not so boring. In fact, yeah, no. Do I still have? Nope, it just completely got rid of it. But yeah. Okay, so VAB equals VB minus VA. VB equals IS times R3 times, I'll just put it to the other side this time, R4, shit, R3 plus R2 on R1 plus R2 plus R3 plus R4, VB equals, again I'm just going to go straight ahead and get the answer. I'm not professional, I do not have one I prepared earlier. Oh, it's so slow working on this calculator. Alright, so VB equals 20.2595, just because I'm like rounding volts. VA equals IS times R3 times R4 plus R1, all on R1 plus R2 plus R3 plus R4. VA equals times 300 plus the 600 divided by 100 plus the 500 plus the 600 plus 200 was 10.3145 volts. VAB equals 20.2595 minus 10.3145 equals, oh shit, no, it's the other way around. No. Yeah, this is right, my bad. 20.2595 minus 10.2145 equals 9.945 volts. And checking this, there you go, that's the answer. Okay, next part. I will skip steps like I did before. So 0 equals, IS is gone, you end up with R4, R3 plus R2 minus R3, R4 plus R1 equals R4, R3 plus R4, R2 minus R4, R3 minus R3 plus R1, times R1, my bad. And R4 and R3s cancel out. Taking this to the other side to make it positive, R3, R1 equals R4, R2, and because they want R2, that bottom left corner one, solve for R2, R2 equals R3, R1 on R4, checking the answer, R3 times R1 on R4, that's exactly what we got. Solving numerically, R2 equals 4300 times 3600, all on 7,500 equals random noises 2,064 ohms. Double check the answer and done. Easy peasy. Alright, on to question 2. I am almost certainly going to make a mistake here, so just bear with me, guys. Basically, what this question wants is V Thevenin, R Thevenin, and I Norton. And basically, what we're going to be doing, we're going to be working out V Thevenin and R Thevenin and using that in an Ohm's law kind of way to get I Norton. It's pretty simple stuff. You'll see. First way to start here is to define your values for G and VC. For VC, we see here, if we just label these V3, V2, and V1, VC will just be negative V3. And GM value is just this one here, so it's negative 8. From here, we just do nodal, nice and easy. V1, we have V1 on, I'm going to get the R1 shit, because I don't really care about it, plus V1 minus V3 on 10. We have our voltage controlled current source going into V1, so it's going to be a negative value, so it's negative GMVC equals 0. Really should have just simplified that as I was doing it, but oh well. Negative 8 times negative V3 equals 0. Splitting this up into its components, we have V1 12 plus 1 on 10 plus 0 V2 minus V3 8 plus 1 on 10 equals 0. We'll leave that for there now. For our V2, we have V2 on 1, nice and easy, plus V2 minus V3 on 24, and our voltage controlled current source is going away, so we plus negative 8 times negative V3 equals 0. V2 1 plus 1 on 24 I'm just going to leave out V1 because you already know it's 0 minus V3 1 on 24, and because that's plus, I'll just do minus 8 equals 0. I've probably made a mistake there. Yeah. Sorry guys. Just don't want to fuck anything up. Plus 1 on 24. This ends up being A to B3. So you have plus B3, 8 minus, 0. And then, we can leave that there for now. I think we can just use this little space for V3. Our voltage source is I1 is going into V3, so it's going to be negative. So it's negative, -1, so it's 1 plus V3 minus V2 on 24 plus V3 minus V1 on 10 equals 0. You have V1, negative V1, 1 on 10. Negative V2, 1 on 24, plus V3, 1 on 10, plus 1 on 24, equals -1. And we have our handy dandy bloody equation solver here. Let's see if I don't screw this up. First equation, 12 plus 10. And through here, 8, 1, nope, just 1. It's negative 0. For the second one, we have 1 plus 24. I really hope I haven't balled something up. Oh, that's the V2, my mistake. Trust me to say, just then. Oh, God, my head's not in at the moment. That's 8 minus 24 there, so 7.95803. Through again. And for the last one, negative 0.1, negative 0.04166, and 10 plus 24, 0.0, oh, no, 14166. And that's -1 there. Computer's screwing up again. Okay, so here are our values here. Still get to see if this is right. As we can see here, our value for Vthevenin is going to be V3 because it's at the A terminal. So I'll just move this over here so it doesn't get rid of it. Vthevenin is going to be 2.52641 E -1. And that is correct. Thank freaking Christ. And now the way to work out Vthevenin is to simply attach a current source between terminals A and B of 1, and then we end up doing yes, my brain's gone. We end up doing nodal again, counting this voltage source going into node A, or node V3, whatever you want to call it, which really only changes one part of the equation. In the equation solver, you just -1 from here, so we end up adding 2 there. Solving again, we get a value for, let's just call it Vx equals 5.0528 E -1, which is just 0.50528. And the equation is Vx minus Vthevenin equals, no, sorry, yeah, on Ix equals Rthevenin. There's an explanation on the Facebook page to that. I asked a question before. But that's basically what you have. So Rthevenin is 0.50528 minus Vthevenin, which is 0.25264. all on Ix, which is the current source that we added, so it's 1 Thevenin equals 0.555 28 minus 2564. Oh crap, it's the other way around. God damn it. My mistake, guys. It's V. But yeah. I might just skip this part. You know what? No, fuck it. I'm going to leave it in. People make mistakes. Okay. The equation is R Thevenin equals V Thevenin minus Vx on Ix. R Thevenin equals 0.25264 minus 0.50528 on 1. R Thevenin equals negative 0.25264 recheck that answer. It is also correct. And using Ohm's law with our values here, VIR in respect to this, so we have I equals V on R. Should be -1. And yeah, it is. Alright, I'm going to do the next question on this one without screwing up this time. And hopefully it goes a little bit better. Just save this one. Q2, B1. New bump. Alright. Yeah. Sorry guys. It's been a long day. We have V1, V2, V3, we have V Thevenin, R Thevenin, I Norton. V1 on 16 plus V1 on V3 over 7. Our current source is going in, so it's -2 equals 0. Simplifying that, gathering like terms. Is that done? For V2, we have no, sorry, I've just ignored my own steps. GM equals -3, and VC is here, so it's also equal to -V3 like the last question. We have negative GM VC, so we'll just work out that now. GM VC equals 3V3, so we have -3V3. Our current source is going out, so it's +2 plus V2 minus V3 on 40 equals 0. Simplifying, we get V2 1 on 40 plus V3 minus negative V3 minus V3 3 plus 1 on 40 equals -2. Now for our V3 node, we have V3 minus V2 on 40 plus V3 on 7 plus V3 minus V1 on 7 equals 0, gathering like terms, and minus V1, 1 on 7, minus V2, 1 on 40, plus V3, 2 on 7 plus 1 on 40 equals 0. Going to our equation solver. First equation, we have 16 16 plus 7, 0.20536. We have no 0, 2, that'd be 2. V3 is just 7, 0.142857. That's with 2 here. For our next equation, we'd have any V1, 40, 0.025, minus 3 minus negative 3.025, and that's negative 2 here. For our last equation, we have negative 0.142857, negative 0.025, 2 on 7 plus 40 is 0.31071 with value 0 at the end. Solving here, we get the value for V3 and also V Thevenin is 2327787. And like I did before, in order to work out R Thevenin, you add a current source here with a value 1 going towards a node, which changes the this is minus 1 to here, because when you end up using this one, you end up having plus 1 here, which goes to this side, which equals minus 1, just in case you guys didn't get it before. Resolving, the Vx equals 0.6152 that's easy, and R Thevenin equals V Thevenin minus Vx on Ix, 0.232787 minus 0.61521 all on 1. R Thevenin equals negative 0.38243. And then using Ohm's law, we have I Norton equals V Thevenin on R Thevenin. So I Norton equals 0.232787 on negative 0.382423. I'll make a note, it's also notes in the help file that with circuits that have a controlled source can have a negative R Thevenin, and that's the only time it'll ever have a negative R Thevenin. If you don't have a controlled source, R Thevenin will always be positive. So if you're getting confused by that, that's just the explanation. And so for I Norton, 0.2327887 divided by 0.382423 equals, you really hope I'm right, 608716. And fingers crossed, guys. What did I do wrong? God damn it. Let's double check. Ah, of course. That is a negative. I am stupid. Yeah, 2163. Yep. Yeah, slightly off for some reason. It's close enough to get you that it's within 1%, it's well within 1%. And then, so if we have 0.21633, I'll do that one. 343. Change that to -1. Minus 0.571751 equals -3.55408, which is exactly this, and just using Ohm's law, get unknown again. Sorry guys. Just yeah, lesson learned. Make sure you check the signs of this, otherwise it'll screw things up for you. Okay, I'll fix this up. Yeah, so that's this question done. How awkward. Alright, it's question 3 for the exam, which is pretty easy. I've done a video on this before covering more versions of this, so you can click here if you want to view that video. This isn't going to be as in-depth as I go in there because there are different variations to this circuit which you can get. Basically what this question wants, it wants you to work out VO and IO, so let's put those up here for now. VO is pretty easy just because VO is directly connected to V2 and there's nothing separating, there's no voltage division or anything. So VO is, because V2 is going that direction, the current is flowing into the node. VO equals negative V2. Don't know why it's V2, there's only one voltage source, but who cares. So that ends up being -5, and IO, if we do nodal at this central point here, we have 0 equals negative IO minus I1 minus 5 on 2000. We have IO equals negative 500 micro minus 5 on 2000, which when we work that out, we end up getting 0.0003 or -3 milliamps. Sorry, 3 milliamps. Looking at the answer, -5 and 0.003, and that's the answer for that one. Let's see how quickly I can swap this over. 2, 3, 2, 1. New. Not looking, not looking, not looking, not looking. This one's slightly different. VO is going to be and IO rather. It'll be the voltage across R2. So VO will be negative I1 on R2. VO equals 400 micro on 1000. Oh, let's just ignore that I did that. I1 times R2 equals negative 400 micro times 1000. So, sorry, that ends up being positive because it's negative. 400 e minus 6 times 1000. Our voltage ends up being 0.4. And simply IO, you do nodal at this point, so it's going to be 0 equals negative IO minus I1. IO equals negative I1, so it's just 400 micro or 0.004 milliamps. I did that correctly. No. Yes, that's right, I think. Just ignore this. just in case that's something stupid. Sorry, an extra 0. But yeah, 0.4 volts and 400 positive microamps, and that's pretty much simple. Again, hit this link using the mouse now. Click for the video covering this better. Yeah, so pretty simple. Sounding so bored. Save this. The next one's pretty easy as well, trust me. Welcome to question 4 for the exam. This one I also have a video for, which you can visit by clicking the annotation in this little box. I'm not even going to bother writing it this time. And this one is just really too easy. You have 2 equations you really have to look out for. So you have your inverting equation, which is when the input is at the negative terminal, and that's negative RF on RI, so your feedback resistor on your input resistance, and your non-inverting is AV equals 1 plus RF on RI, and your overall, your gain is going to be AV times AV. Very, very simple. So if we work out for AV1, the resistance is, we see that it's a non-inverting because the input is going to the positive terminal. Then it's going to be 1 plus R4 on R2. AV2 is going to be, it's inverting because its input's going to the negative terminal, ground's going to positive. Positive's going to ground, whatever way you want to see it. It'll be negative R3 on R1, so that'll be 1 plus R4 on R2 times negative R3 on R1, bring the negative out front. And that's your overall gain right there, nice and simple. Working out the numeric value for that is just as simple as inputting your values. Oh god, I'm so hungry. R4, 18,000 on 3,900 multiplied by 62,000 on 1,500. And that gain ends up being negative 232.1026 volts before. We look at the answer here. I think it's this one. That's, yeah, 256. For the second one, let me just save this. Not looking. Whoops. Let's try that again. We have AV1 inputs into the negative terminal, so it ends up being R3, negative R3 on R1. AV2, the input's going into the positive terminal. And if you're getting confused where your input and input resistance, looking at here, I always remember it by your RI is the resistance that is attached to the feedback resistance. So if you're thinking, oh no, there's no resistor here, what the hell do I do? Just ignore that and look at whatever the resistance is that's attached to your feedback resistance will be your RI. And looking at that, we have it's positive, so it's 1. That's a it's non-inverting, not positive. R2 on R4, those together equal negative 1 plus R2 on R4, R3 on R1, which equals 18 divided by 1, 20 divided by 1, what's easy? Negative 380 volts per volt. Looking at the answer, you can see it is symbolic would be obviously the same if we get the same numeric value. Cool, nice and easy, much quicker than the other ones. Alright, now to possibly my favourite question, because it takes so goddamn long to do. It's annoying, the amount of numbers that you have to deal with. And go figure, maths, right? Yeah, the 3 diodes question, which you're probably all very familiar with by now. Whether you actually remember how to do it is another thing altogether. So, first thing you want to be doing, first step, is to figure out whether D1 and D2 is on or off. The easiest way to do that is to look at the polarity of V1 and V2. V1 is positive, so that means the current will be, the voltage, or current, whatever you want to talk about, is flowing this way. And it's going from ground through V1, R1, D1, R4. And it's following the same route. D1 is pointing, so D1 is on. D2, V2 is negative, so it's doing the opposite thing. So going from R4, D2, R2, V2. It's going the same way D2, and D2 is also on. Okay. Excellent. Now, from here, it can get a bit hairy if you screw up numbers, but overall it's pretty easy, so you don't have to worry about it too much. Yeah, so to work out, you need to work out voltage at R4 so that you can determine whether D3 is on or off. Because D3 is pointing into the node, if R4 is a positive number, D3 will be off. If R4 is a negative number, D3 will be on, because obviously 0 flowing to negative will obviously have the diode on, and if it's positive, it's greater at the cathode and it is off, because it can't flow backwards. It's a diode. The way to figure that out is just to simply use superposition at R4. Well, I think it's superposition anyway. You end up having the voltage going through here, and the voltage going through here, using voltage division between R1 and R4. So you end up having V, we'll call it VS1, I don't know why, equals V1 times R4 on R1 plus R4. That gets the voltage at R4 from V1. VS1, I'll just work it out. 11 times 110 divided by 17. 16? No, 17. 10 equals 0.70760 volts. And VS2 equals -9 times 110 divided by 3410, because it's V2 times R4 on R1 plus R2 plus R4. That equals -0.29032 volts. And to work out, because it's superposition, you just literally have Vm equals Vs1 plus Vs2, and we know because Vs1 is obviously a greater absolute value than V2, it's going to be a positive number. We don't have to work that out. So we know D3 is off. From here, Now that we know the states of all the diodes, we can work out the overall voltage at this node using nodal. This is short circuit, this is a short circuit, this is an open circuit, so we don't have to worry about this. And at that node, 0 equals, we'll just call this V for now. V on R4 plus V minus V2 on R2 plus V minus V1 on R1. And now we're just solving for V. This is going to be a long-winded process because I prefer dealing with larger numbers. V on 110 plus V plus 9 on 300. I'll probably speed this bit up. $1,600 times 1,600. Yeah, basically what I'm doing here is that I'm going to be doing cross multiplication to get rid of the denominator. The overall denominator will be 110 times 3,300 times 1,600. Skipping a step, I'll end up with 3,300 times 1,600 times V plus 110 times 3,300 times V minus 11 plus 110 times 1,600 times V plus 9 with no denominator because it cancels out when you multiply it out. Grouping the symbols, we end up having 5280000 plus 176000 plus 363000 gives us 581900V. And I don't know if this is going to be minus. It's going to definitely be minus. 17600 times 9 minus 36300 times negative 11. No, times 11 because it's already minus. 240900. B equals 2409 on 519. B equals 0.4139. Now, 9, just because it rounds up with the next bunch of decimals. Okay, you may notice that this will be the same as with the VM that we've calculated here. So if we do 0.70760 minus 0.29032, we end up with about the same value. The reason why we don't use this value is because it changes. It can change dramatically if D3 is on. So following this process is guaranteed every time, if you follow it properly, to get the right answer. And basically, just to get the currents going through D1 and D2, we just refer back to these equations that we got for nodal. And ID1 is going to be 0.41399 minus 9, so plus 9 on R1. Oh shit, no. Let's try again. Minus 11 on R1, which is 1600, on 1600, 0.41399 minus 11 divided by 1600. And now I'll point out now, you have to have the absolute value of these because you can't have a negative current going through a diode because the diode is unidirectional. It's a negative 6.6163 milliamps, but the absolute value makes it positive. ID2 equals 0.41399 plus 9 on R2, which is 3300, equals 2.8527 milliamps. And we'll check against our answers. So yep, 6.616 to the negative 3 and 2.85 to the negative 3, which means our answer is correct. And obviously D3 is off, so ID3 is 0. And yeah, that's correct for the first one we've done. Let's just save this one. And this is question 7 of the exam. At this point you may be thinking, why James, at the start you mentioned you were going to do both examples from either exam, favourite question. And my response to that is, for question 6 on the second exam paper, I kind of fucked up the answers and I really can't be bothered going through them again. I've got plenty of explanations up on the Dropbox on how to do it, so yeah, if you need any extra help, you can either post a question on the wall and I'll answer that if I can, or you can just read the documents. Pretty simple. Anyway, moving on. Question 7's last one, lucky last, thank freaking Christ. Probably the most annoying depending on the configuration you get. Hopefully we all get one with the switch at the start, opened and then closed. Even if it's closed and open, it's not too bad. But basically what we're looking at here is charging capacitors in RC transient circuit. It's been opened for a very long time, so that this has become an open circuit. The capacitor has not been charging, so at VO negative just before it closes, our capacitor charge, and thus, well, there's no voltage going through, so at VO the voltage is 0 volts. And when it directly closes at VO, there is also no thing. VO plus, because it doesn't get the charge, there's no voltage as well. It takes time to charge, obviously. Skip VOT for now and then go V infinity. That's just going to be the maximum charge C will have when the switch is closed, it's short circuit, so we're using both R1 and R, using voltage division between R and R1. What the charge through the maximum charge of the capacitor is going to be the voltage going through R, maximum voltage going through R. So voltage division VO, let's just fix it up, equals VS times R on R plus R1, which is equal to 10 times 1200 divided by 11200. 1.07143 volts. That's V infinity. And I'm going to do something different. Farid put up notes that he wrote during the lecture for the golden formula for transient response questions. And I'm going to, that's this one right here. I'm going to be using that to see if it actually works. If it doesn't, you've wasted my time, Farid. So I'll be coming for you. But we'll have our fingers crossed for now. Basically, we want the charge at a particular time, in this case 4.7 microseconds. Ignore the stupidity of paint right there. And so V for 4.7 micro equals V infinity, which is 1. Plus VO, which is 0, minus 0.07143 E, negative 4.7 10 to negative 6 on tau, and our tau equals R equivalent times C. And if you look at here with that closed, R1 is in parallel with R, so our R equivalent is going to equal 1071.43. It's 428, but we can just leave it for there. Multiplied by C. I do this just because it makes it easy to put into the calculator, so you don't have to worry about brackets and shit. Times 4.3 e negative 9. Equals 4.607 is negative 6. Just add another one there for the hell of it. Okay, so that's our tau. So that means we have 4.6071 10 to the negative 6. And these cancel. So when you shove it in our calculator, we get the answer, fingers crossed, for read, plus minus you can do 4.7 divided by 4.6071. Ooh, lucky, lucky, lucky. You get the answer 0.68514. And that's our VT. Check that against the answers we have here. Oh, that's the wrong one. We have 0 and 0 for V 0 negative and 0 plus. For infinity, we have 1.7142 round up to 3. That's fine. And for our VT, we have 0.6813 up, rounded up to 4. Voila, done. Okay, so that's that one done. Q7, P1. Lucky last. Not looking. It's always good to put down your equations. We'll just have it here. V T equals V infinity plus V0 plus minus V infinity E negative T on tau. Okay, so same deal. Let me just copy this. It's been opened for a very long time, so no charge for the capacitor at VO negative equals 0 volts, and as soon as it closes, the capacitor still doesn't have time to charge, so it's still 0 volts. At V infinity, we have the the voltage division between R and R1, so it's Vs times R on R1 plus R equals 12 times 3600 divided by 4900. 8.81633 volts. Now VT equals 8.81633. That's messed up 3 because 0 minus 8.81633 is the negative, what is it, 1.1 10 to the negative 6 over tau. Let's calculate our tau equals R equivalent times C. R equivalent equals 600 times 1300 divided by 4900, because they're both in parallel, 955.102. Now tau ends up being that times 1.2 to negative 9, 1.146, 10 to negative 6, so we have 1.146 there, 10 to negative 6. The powers cancel, so solving for that, we end up getting 8.81633 minus 8.81633 e to the negative 1.1 divided by 1.146, and that is 5.4401 volts. Checking that against our answers, 0, 0. It's reasonably close. Probably should go to. It's kind of strange how it's not that close, but that's within 1%, so you don't have to worry about that. And obviously 8.81632. And voila, that's pretty much it for the rest of it. Whew, let's just hope that they don't change the questions on us, hey? Good luck, guys.